Okay, in the last lecture, I introduced the Kuhn model. So basically what we did was we parameterized the chemical details like a bond angle, a dihedral angle, and the specificity of these barriers for rotation around a bond, etc. in terms of segment length, namely Kuhn length, we call Kuhn length. So we imagined correctly a real chain can be imagined to be made up of freely jointed segments of length L, and there are n of them. There are n such segments. And this is a freely jointed. Then we argued that if n, the number of segments, is very large, so that means what? That means the contour length of the chain, contour length, say that is L, let me write L as a contour length, that's equal to number of segments times of number of segments times little l, because I have every segment has a length L, one segment, second segment, third, so there are n segments, therefore contour length is n times L. If contour length is a much larger than segment length, we said this is a Kuhn chain model. Kuhn model is called a Gaussian chain. That's what we argued. That's a Gaussian chain. Right. Why do we say it's a Gaussian chain? Because we say that the probability for this chain to have end-to-end distance R after n such steps, and as I pointed out, there is no extra volume interaction. That's a subscript to 0. That means I do not have interaction between this segment and that segment. Inter-segment interactions are not allowed. Only the skeletal structure is accounted for in this model. For that, we argued it's a 3 over 2 pi n L square over 3 by 2 e to the minus 3 R square over 2 n L square. Okay. And this is a Gaussian function. It's e to the minus R square. It's a Gaussian function. The important thing to recognize here is R is end-to-end distance vector from one end to the other end. And n is the number of segments. And as you know, capital N is proportional to little n, number of actual repeat units. Therefore, capital N is proportional to molecular weight. So in these lectures, I will use capital N interchangeably with the degree of polymerization, molecular weight, etc. And based on this, we got the following important results. What we got was exactly in this limit, R square without any extra volume interaction is equal to capital N L square, which we could rewrite to be capital L times little l. Same thing, because capital N times little l is the contour length L, which I have shown in here. That's my contour length. The important thing is this, I could write to be something like proportional to the molecular weight power or degree of polymerization power or number of Kuhn steps of power. I'm going to write this to be 2 nu. where exactly nu in this particular case is equal to half. Nu is equal to half. This is mean square into distance. And we also pointed out Rg naught is equal to n L square divided by 6 square root. And this is proportional to n power nu. Again, of course, naturally, nu is equal to half. We also found out, I showed you, the form factor which can be determined using scattering techniques. S of k is equal to, I wrote down this to be 2 n, I'm interested in this. Let me use a different symbol here to highlight the important thing. Oh, sorry. Okay. So the nice thing about this formula is we call this to be Debye structure factor, which we'll return to this in about 30 minutes. The important thing about this theory of a Kuhn chain model is I have a formula for the form factor which contains information about the degree of polymerization of the polymer and the size, the radius of gyration of the polymer, which is in green, and the degree of polymerization is n. So if we can measure this form factor experimentally using this scattering wave vector k, then we are in a position to determine the molecular weight and the radius of gyration. So we are able to characterize a polymer that we synthesize in our chemical laboratories by using scattering technique. So this is a very beautiful way to characterize a polymer. Now, if you were to do additional techniques like a GPC or mass spec and things like that, we will not be able to get this information so easily. So this is a very effective way. Scattering is a very nice way to characterize the polymers once you synthesize them. So the key, the most important formula that we use in characterizing polymers using in dilute solutions using scattering techniques is this formula. So that's why I'm repeating the importance of this formula. Okay, now let me go to macroscopic properties. So this is a summary of microscopic properties. That is, okay, I'm looking at a single molecule, right? What is the mean square end-to-end distance? What is the size? And what's the form factor? But I like to look at some thermodynamic properties of this Kuhn chain model. And that's what I'm going to do the next, right? It's all in the handout, which I gave you before, but let's do thermodynamic properties, because what I'm going to show you is going to be simple, but extremely useful. We are going to use these ideas of a single chain even later on when we talk about rubber elasticity, crystallization properties under flow. All these things are going to be important. So I like to lay down the foundation very clearly so that we are all on the same page, same platform. Therefore, we could use these ideas towards applications or expansion into new directions in polymer physics. Okay, so how do we do this? We all know that the free energy of any system is equal to, let me write down in a different color, if you don't mind. Free energy of a system is equal to, let me write the energy part, E minus, and I'm going to write temperature, and I write entropy. This is a basic formula, right? This is the free energy of a system. This is Helmholtz free energy, if you like. I'm not talking about Gibbs free energy because I don't have any pressure, Helmholtz free energy. When we talk about a flow and crystallization under pressure, elasticity with some external force, then we have to worry about Gibbs free energy at that time, right? When you have pressure, etc., we have to talk about Gibbs free energy. But right now, we're going to talk about Helmholtz free energy. Now let's look at how do we get an expression for this? First of all, let's say E. What is E? E is the energy, right? And remember, this is a freely jointed chain. That means I have a chain like this, a segment like this, another segment like this, another one like this, another one like this, another one like this, another one like this. There is no interaction between the segments, right? Maybe I should write there is no extra volume interaction. Therefore, I'll put the 0 subscript there. If that's the case, the energy is equal to simply n number of segments times the energy per segment. This is energy of one segment. That's the energy of one segment. It's some number. You can, depending upon the chemical details, there is some energy associated with that. But please notice that does not depend upon end-to-end distance, right? That doesn't care because this is the energy of that, this is the energy of this. I'm just adding them up, but it has nothing to do with the capital R, right? So now what I'm going to do is I'm going to calculate the entropy, all right? The entropy part, how do we get entropy? Entropy for a chain with end-to-end distance R. That's what I'm interested in. So I must have noted down this free energy is for some end-to-end distance R. Right? That's a free energy chain with some end-to-end distance. So what is S? S, is this a famous formula, right? Boltzmann constant times logarithm of a P of R. Or N if you like, P of R N. Logarithm of the probability times Boltzmann constant is giving me entropy. Now let's take the previous formula for P here. There are two factors. One is the 3/2 power of this argument, and another one is exponential. And as you know, logarithm of a product is equal to logarithm of one factor plus logarithm of the another factor, second factor. Therefore, this formula will turn out to be this S of R is going to be equal to, you can do this, KB, that is 3/2 Boltzmann constant, right? Let's look at this, 3/2, look at this formula here, 3/2, logarithm of something power is that power times the logarithm of that. So 3/2 times the logarithm of that, right? And then I multiply my KB. So this is going to be 3/2 pi n L squared. That's one factor. The other factor is logarithm of this exponential. Logarithm of exponential of x is x. So I get negative 3 KB R squared over 2 NL squared. I just simply copied it. All right, this is a logarithm of exponential. That's going to be minus 3/2 NL squared times R squared. All right, and then I multiply by KB. Okay, so that's my entropy. If that's the case, let's substitute this back into this expression. And as you notice, this E is a constant. It does not depend upon R. This one is also does not depend upon R, capital R. That's also going to be a constant. So only the R dependence for the free energy is coming from this term. Therefore, I will write the free energy is equal to constant, right, times minus the temperature times this factor. Negative times sign here, negative sign here, that gives me plus 3 kBt over 2NL square R square. This I wish that you folks will remember, right? This is a very important formula. Why is it important? I have a macromolecule. According to this Gaussian chain model, if I were to plot the free energy as a function of R, free energy as a function of R, it is Hookean, right? It's quadratic in R. So it goes like this. It's a parabola. So this is almost like a spring, a Hookean spring. You have a spring and you stretch it, right? It's going to be hard to stretch. Stretch it harder, it becomes harder and harder in real world, like if you have a metallic spring. But the important factor is this goes like R squared. But you know the spring constant. So this quantity would be called spring constant. So how easily you can stretch is contained in this factor. So this is where the magic of polymer world came about. Polymeric material worlds came about. Because look at this factor N, this is factor N appearing here, degree of polymerization, right? When I increase molecular weight, the spring constant becomes smaller because spring constant becomes 1 over N. Therefore, when I have a polymer chain, a longer and longer polymer chain, then it's easy to stretch, right? This is a very beautiful consequence of the Gaussian chain model. Right away, we are able to capture one of the most important properties of a polymer molecule. This is how we are able to make materials like, you go to a grocery store, right? You are able to stretch certain things, right? We can put some materials there without breaking. The bag is not breaking, but the bag can extend, can stretch, right? That's because the spring constant is smaller when you increase the molecular weight. And of course, it depends upon temperature, right? As you can imagine, when you increase the temperature, the monomers can move easier, therefore it can stretch easier. That is not a surprise. But the important consequence of this formula is the spring constant is 1 over N. This is true, please remember this is true in this region. When R is large, this is true. Okay. But now this is a very simple argument, right? But if you actually do this calculation properly, what you get is a slight modification. Because the problem here is, right, if you look at this formula, look at the minimum of the free energy. The minimum of the free energy is taking place at 0. R is equal to 0. The minimum is at R is equal to 0. That does not make sense to us, all right? Because the free energy minimum is when R is equal to 0. This is what you will see in all textbooks in polymer physics. You will see that. But it's not quite right. Why it's not right? Because you worked it out already. The mean square, on an average, the mean square distance or radius mean square distance goes like NL square. That is, root mean square distance goes like square root of N. Similar radius gyration goes like square root of N, but that's not 0. This is an equilibrium calculation, right? That's not 0. So, but the textbooks will tell you according to this model, this is minimum at R is equal to 0. That does not make any sense. Because imagine I have a ball of wool, I stretch it, there is a spring constant, but take this ball of wool and then I compress it, right? In any of the experiments that you want to do later on, right? When you compress it, it's going to resist compression. It cannot be behaving exactly like an expansion of the chain. It would not happen, right? So careful calculations would show when you do this proper calculations, the free energy actually looks like this. Free energy is equal to, I will write it same as some constant, right? Some constant. This is free energy when R is equal to R equilibrium, okay? Which is some number plus, okay, this is a number, this is a constant, right? This is the minimum free energy, right? That's going to be some constant, which we'll figure it out. Plus, what you'll have is it's the same formula, 3kBT over 2 R square over NL square. And that's what I wrote down here. So far, I did not change anything, right? Some constant I have written, that is the value of free energy when R is equal to, maybe if it's confusing to you, I can simply write this to be a constant. Okay, don't worry about that, constant, all right? Plus, I have written 3 kBT by 2 NL square R square, which is that term. But the additional term, which when you do proper calculations, it was done by Flory long time back, and I did it myself later on in a different methodology with using modern theoretical technologies. But the answer is the same. The answer turns out to be, I'll have a -1 minus logarithm of R square over NL square. That's the formula. So I say more careful calculation gives that formula. Okay? And as you can imagine, when R is very large, that is when R is very large, then what happens is when R is large, this term is going to dominate over this term. So there is no problem here. So in this expansion of the coil branch, where the chain is, I'm just stretching it out, this formula is okay, right? This formula is okay. But on the other hand, this is a problem, right? So when you plot this properly, what you get is, here is free energy as a function of R, right? And you get a curve like this, right? Again, just a parabola like this, but it's a very steeply, when you compress it, it's a steeply increasing. The free energy is, when it resists compression, and this is your R equilibrium. This R equilibrium, right, if it's the end-to-end distance R, that's what we are talking about. This equilibrium is equal to square root of N times L. Okay, this minimum occurs in here. So in a practical purposes, when you do your computer simulation, when you do analysis of your data, when you do experiments, I hope you will remember this free energy formula, because this is the correct formula. Okay, and yeah, and the textbooks don't talk about this, except of Flory's book, 1953 book. He mentioned tiny bit, but all the modern books, they missed the important point that the equilibrium is exactly at this point for a Gaussian chain. Okay, given this, we can calculate the tensile force, right? Because many of us are going to be interested in taking a chain and then stretching it out. Okay, one end in here, one end there, and I'm going to stretch it out with some force. Right? How do we do this? We're going to stretch this force, right? A stretch is polymer chain. Because imagine I have a polymer chain laid out in my system, and with an AIFM chip, I'm going to pull it. I hold on to one end and then I pull it. Or you make an amorphous material or a semi-crystalline material, and then I'm going to pull one end of the chain, for example, anyway, extensional flow or a stretching, biaxial flow. Suppose I do this. What is a force based upon this model? This is a good Kuhn chain model. And as you know, the force is equal to, you can write it to be modular, I'm going to put modulus, is equal to dFr by dr. Okay. Where the free energy comes in here. I take this free energy and I take the derivative of this, and that is my force. So if I take the usual, when this dominates, this term dominates, then this force is equal to, I'm not putting the vector anymore, that force is equal to, again, 3 kBt divided by NL square times R. Again, going back this, right? I take the derivative of this, dF by dR. There's a factor of 2 here. So derivative of R square gives me 2 times R. That 2 kills the factor of 2 in the denominator. So I have 3 kBT by NL square R. Okay, so this is, again, I'm repeating myself. This is my force constant, right? This is my, again, same as before. This is my force constant by, force, yeah. Force constant, you can write it related to force constant within the factor of 2. But in general, of course, I can take this one in general for this model. This F is equal to take the derivative of this, right? We already have 3 kBT by 2. 2 kills that one. So I have 3 kBT over, the important factor is, right, 3 kBT over, let me write down, maybe I should write down 2, right, 2. And then I have 2R over NL square, right? And then -1, derivative of that goes away. This is minus log R square. That will give me -2 log R derivative, that's 1 over R. This is a constant. Okay, so that will give me -2 over R. Okay, and of course, it is a 2 will cancel out. Then what you get is, right, when you do this, what you get is simply a very simple formula. I can rewrite this to be 2 cancel out. So I will rewrite this to be this is right. Yeah. So I can rewrite this to be 3 kBT, right, by little l. Let me write down R over NL, right here. R2 cancels out. I'm taking 1 factor of L out. Therefore, I'll write this to be L over R, so that I have the dimensions right. The Kuhn length on the top, R is the length, end-to-end distance length. And then this is the end-to-end distance Kuhn length at the bottom and N. So this is a general formula, right? This is really fantastic, right? If you plot this force, what you will see is for the expansion region, you'll get this results. When R is very large, capital R is very large, then this is negligible. Therefore, this dominates, I get this result. But when R is small, this becomes important, 1 over R, right? That becomes very important with the negative sign. Then the compression force, if the force acts in the opposite direction. So here is the expansion force operates in one direction. When I bring R smaller and smaller, into and smaller, I'm compressing it, then the force operates in the opposite direction, okay? But this is not the complete story, right? This is not complete story, because the reason why it's not complete story is the following. Let's think physically, right? Maybe somebody can answer me. Maybe I'll pick on June 5. So I take this chain, according to this model, right? The force, suppose I'm expanding in June 5, right? When I'm expanding it, the force is proportional to R, okay? So that means what? If I write the force, let me plot F L over KT. This is the reason why I picked out this L. F L by KT. That's what I'm plotting. And this is F L by KT. And then I'm plotting as a function of R. Okay. Let me plot as a function of R over NL, maybe. R over NL. That is going back to this formula. This is R over NL. So I take 1 factor of L here, FL by KT, and then R over NL. So this is 3. So that means this tells me there's going to be a straight line like this. This is for a Gaussian chain. Okay, that's the prediction for a Gaussian chain. When R is very large, right, it is a Gaussian chain is a straight line. Is it physical? I take this chain, right? I hold one end, and I take the other end and I pull it, right? I keep on pulling it, right? Keep on pulling it. And then can I go? Remember, I told you the contour length. I told you the contour length is NL. That means, right? It cannot go beyond the contour length, right? It cannot care. According to the Gaussian chain model, what it tells me is it can go R over NL is to say, let's assume it's 1 here, right? It says, according to the Gaussian chain model, even when R over NL is infinity, right, I can stretch it, right? Do you understand? That's what this formula says. And that's not right, okay? What happens is it has to cut off, right? And so if you actually, right, there must be, this is not applicable on physical grounds, this is not applicable, this model is not applicable for R greater than NL. In real world, what happens is, it goes like this. So when you stretch the polymer chain, when you go closer and closer to the contour length, you cannot stretch it anymore, right? Because the force becomes, unless you break the bond. So the force becomes infinitely large, right? So this is the case for freely jointed chain, right? This is the model that we are doing. This is the Kuhn chain model. This is the Kuhn chain model. This is the Kuhn model, actual Kuhn model. So the difference between this curve and this curve, what is the difference? The difference is in here. Difference is here. That is, I said, only if contour length is much larger than L, only under those conditions, we get Gaussian chain model, right? But if the contour length becomes comparable to the end-to-end distance, this formula is not right. This formula is not right. This formula is right only if, right, this is true only if R is greater than NL. I'm the other way around. The R is less than NL. R is less than contour length. Let me put it there. R is less than contour length. So the Gaussian chain model is valid for the two conditions. One is this condition. That is one condition. Other condition is end-to-end distance is less than contour length. Under only those two conditions, this Gaussian chain model is valid. And this is an important criterion that we need to register in our strategy, right? We cannot apply Gaussian chain model for every problem that we do. Only under these two special conditions that is true, particularly if you want to compare with external data. But if you go into this situation where I break down, I do not say any such things. This is only for this Gaussian chain model. Maybe I'll write in a different color. This is true only Gaussian chain model is true when R is less than, yeah. Strictly speaking, that's the way we compose our model. That means this is valid only in this region. See, R is less than L. Then the actual Kuhn chain model and this Gaussian chain model, they are the same. The answer is the same. So in the limit of R less than L, capital L, contour length, then it's okay. But if you're stretching more and more, then you have to use this model, the actual expression, not the Gaussian chain expression. Now I like to also introduce one more model before going to the consequences of this structure factor. Before we go and look at this one, I like to add one more model. This model is called a Kratky-Porot chain model. Kratky-Porot chain model, or it's also called worm-like chain. Worm-like chain. It's also called worm-like chain model. Right. So what does that mean? That means that, okay, I have again, it's more like a Kuhn chain model, but except with one caveat. Right. So you take a segment, Kuhn segment like this, and because of the local barrier, rotational barrier, it doesn't completely fold back, right? That's not allowed, right? Instead, it makes a little bit of an angle there. This is my theta. bond angle. It doesn't completely rotate back, very tiny small angle, because now we are talking about Kuhn segments, right? We are not talking about single monomer, right? So then the next one may be like that, right? And maybe like that, and on and on. So if you have a model like this, you can work out the calculations, and then you find out the R square, no extruder volume effect yet, only along the chain backbone. Then R square is equal to 2 LP times capital L. L is the contour length. Okay, I'll tell you in a minute what LP is. 1 minus LP over capital L, 1 minus e to the minus L over LP. Okay. To emphasize the importance of this formula, maybe I will write the different color. This is LP. This is LP. This LP is called persistence length. Okay. Now, clearly, if that is what is persistence length? That is the distance over which the orientation of one bond persists. Distance along the chain contour over which bond orientation or segment orientation. Let me write bond orientation persists. That is, so you can, as you can see that, right, this orientation of the bond is a persisting here. So now locally, there is some persistence length. Remember, I introduced this idea of persistence length in my first lecture. It is related to, if you remember, it's related to the delta epsilon by kT in terms of rotational, between the gauche and the transit states. So this is a measure of how the bond orientation persists. But if the chain is long enough, if the contour length is much longer than LP, then this will eventually fold back, something like this. When it folds back, right, the chain will be folding back, and then this orientation is not going to persist. So for long distance, it will be like a coil-like, and for short distance, it will be rod-like. That's what we imagine intuitively. Let's look at the consequence of this formula. All right. If capital L is very large, the contour length is very large compared to the persistence length, e to the minus large number is 0. E to the minus large number is 0, right? Then, and then 1 is bigger, and then LP over L. L is larger than LP, therefore this is small in comparison to 1. So what I get is 2 times LP times capital L. That's what I get. On the other hand, if capital L by LP is small, then I can expand this exponential. E to the minus x is equal to 1 minus x plus x squared by 2, etc. And then when you substitute this, you'll get the following results. Therefore, according to the Kratky-Poulard model, R square average, no extra volume effect, is equal to 2 LPL. Okay, this is for L much larger than LP. If the contour length is very large compared to persistence length, that's what we get. On the other hand, if we are talking about the other limit where L is smaller than LP, right? Then by expanding the previous expressions, you will get L squared. This is a very nice formula, particularly for semi-flexible polymers. This formula is an important one. Without consideration of extra volume effect, this is an important formula because what this tells me is, look at this, L is a contour length, end-to-end distance square is L square. So that means that this is a rod-like. This is rod-like. Because for a rod, straight rod, the end-to-end distance is contour length. So the average end-to-end distance square is contour length square. On the other hand, here, this is the Gaussian chain result. Remember, we talked about n L square. All right, I told you here, yeah, capital L times the little l, L is Kuhn length, right? R square average is equal to capital L times the little l. That's a Gaussian chain result, right? So that's what we get. We get this is equal to capital L times the little l. So that's the Gaussian chain. Gaussian chain. This also means, right, 2LP, 2 times LP is equal to little l, right? Remember the Kuhn length, right? The Kuhn segment length that we defined for the Kuhn model is precisely 2 times persistent length. Okay, so 2 LP is equal to Kuhn. This is Kuhn length. And obviously, this is persistence length. Okay, so this is something that you may want to remember in terms of reading the literature. So when people talk about when you want to report your XML data or appreciate somebody else's XML data, you can think about what is Kuhn length, what is persistence length. Once you know Kuhn length, it also tells you how much along the backbone of the chain you have persistence of bond orientation. Right? So at this moment, I think I'm going to stop here. If this is okay, I'll stop here, and then we'll take a small break, and then we'll continue. Is that okay, June? June, fine?
Do we have 5 minutes break?
Yes. Thank you. Fang, are you there? Jun Fang, are you there?
Hello, Professor.
Hi.
If we need to start,
I need what?
could we start now?
Yeah, we can. Whenever you are ready.
Thank you.
Sure. Okay, so, all right. So let me go back again. Right, let me go back again, remind you about, so what did we do? So we did a lot of things, right? Single chain, we did single chain. We talked about the Kuhn chain model. We got the probability distribution function, and this model is valid under some limiting conditions, but nevertheless, that's a very common condition. Then we got an expression for the structure factor. We got an expression for structure factor here. And then we talked about the free energy. And then from the free energy, we got the force, right? So we have a complete description of what this chain is doing, right? And I want to remind you again, if you can see me, right, the Gaussian chain model is a freely jointed chain, right? Kuhn chain model is freely jointed, right? Can you see me this? Can you see this, right? It's the chain of paper clips, right? There is nothing going on, right? It's completely flexible. But if I lift this one and I'm making sure that they are locally stiff, if I do that, locally stiff, it cannot bend and rotate freely, then we got into the Kratky-Porot chain. That's what we did, okay? But now I want to go back to the flexible chain, Gaussian chain, right? When I go back to the Gaussian chain, once more, I'm going to write down the formula for the structure factor. The formula for structure factor, form factor, S of K, where K is equal to 4 pi over lambda sine theta by 2, right? So this is an experiment that we do. So here is some sample here, and then we have an incident being with a wavelength lambda, right? And then I measure at some scattering angle theta. Here is a detector, and then, oops, I measure, here I measure the scattering intensity I of K. This is scattering intensity. This I of K is proportional to S of K, which is the form factor. I'm talking about single chain, right? Therefore, I'm not worried about interference between different chains, solutions, which we'll talk about down the road, 2 weeks from now, right? So I measure this, right? This is experiments. And this one is a theory. This is a connection between how we interpret the data, how we use the theory to interpret the data that you make measurements, and also how you validate a theory by actually making measurements to say, oh, this theory is bad, et cetera, right? And according to the theory, we had this device structure factor. Device structure factor. Okay. And what does it tell me? That tells me, again, I'm going to write it again for convenience. S of k is equal to 2. There are two important quantities, 2n by k to the 4. Incidentally, in some books, instead of K, they'll be using Q. Okay, it's only a symbol. Right? In some people instead of K, they will write I of Q, small letter Q. Some neutron scattering, they use capital Q. But as long as you know what that K means, a scattering wave vector. Okay, this K, this is a scattering wave vector. That's what you need to know. As long as scattering wave vector. Okay, so now let's see what this tells me. This tells me, I think I need some help from some of you folks. Let me take K times RG is very large. Okay, I say K square times RG square, right, is much larger than 1. Let me take that limit. That means what? E to the minus, this is a large number. This is a large number, right? E to the large number is zilch, nothing. It goes away. And this is a large number in comparison with the -1. Therefore, this is important. When this is important in this parenthesis, that's going to kill a factor of K square RG square. Therefore, I get K square times RG square overall. In the numerator, 2n. But RG0 square, you know the answer. I wrote it down even today. Here, RG square is capital N L square by 6. When you take the square, it is N L square 6. So I put that back in here. And then I will get, what you get is I get 12 divided by K square L square. Okay, in this limit, I do not see the green symbol or red symbol, right? Because I don't see a red N or a green RG0. In this limit, if I'm in that limit, I don't see molecular weight, I don't see the size of the polymer. But on the other hand, if I'm in the other limit, namely K square times RG0 square, is much smaller than 1. Suppose I'm in this limit. What do I get? I take this exponential, I expand it. The leading term is 1, right? 1 minus x plus x squared by 2. The leading term is 1. That will cancel this -1. The next term is minus K square RG0 square. That will kill this term. And the next term is K to the 4, RG to the 4 divided by 2. That will kill me this K to the 4, RG to the 4 divided by 2. That 2 will cancel out. And then the next term is going to be, right, K to the 6, RG to the 6 by 3 factorial, that's a factor of 6. So when you do this, what you get, right, when you simplify this, what you get is a very important formula. N times 1 minus K square RG0 square divided by 3 plus etc. etc. That's what you get. When you expand that exponential and simplify it, the leading term is the n, right? N power 1, n is a factor, then 1 minus K square RD square by 3 plus etc. You get this result. This is really fantastic, right? Why is this fantastic? because this gives me an opportunity to measure the molecular weight and also molecular size. We can measure RG0 and molecular weight. We can measure that using this one, because we know that this can be gotten from experiments. We measure the scattering intensity, and then from there, using your instrumentational setup, you can get the form factor. And then from the form factor, you can get molecular weight and the radius gyration. And there's a big if. We can do this only if, only if this condition is satisfied. If this condition is not satisfied, we will not be able to do that. So you have to, when you make the measurements and when you want to interpret your data, you must ensure that this condition is satisfied. If you are interested in getting molecular weight and radius gyration, this is a very critical condition. And how do we do this? Okay, so what I'm saying is, I'm saying K square RG0, RG0 square is a much less than 1. I'll be able to measure size of the molecule and the molecular weight. On the other hand, in this limit, I don't get that information. I get some other information, but not molecular weight or radius gyration. Okay? So this gives me an idea. All right? The idea is the following. Right? This gives all of us an idea. Okay. Right? The idea is, let me go back to this expression. Right? This quantity, I of k. Suppose I take, I'm giving you as an example. Here is a lambda, right? For example, suppose the source, scattering source, suppose it's the light, right? The wavelength typically is about 500 nanometers, right? And if it is X-rays, the lambda is about 0.15 nanometers. Right? And then if it's neutrons, lambda is about, again, 0.5 to 2 nanometers. So going back to this experiment, right? Going back to, here is my sample, and here is my incident beam lambda, and then this is my angle theta. And I'm repeating myself, K is equal to 4 pi over lambda sine theta by 2. So going back to this expression that we got from the device structure factor, we can make a successful experiment only if we can satisfy this condition, right? Otherwise, we won't be able to do it. So it's not good enough to have a fantastic instrument in my backyard, right? But right, that's not good enough. What we need is how to use that instrument in the appropriate situation. How do we, if we have a goal of determination of something, we want to be able to use that instrument appropriately. How do you do that? And the idea is this. Suppose I have, okay, so I'm telling you here, right? There are two combinations, right? One is this lambda term. The other one is this theta term. So we can use lambda and theta appropriately, a combination of them, to tune K. So it can tune, you can choose the wave vector, scattering wave vector K by a combination of the wavelength of the incident beam and also scattering angle. For example, if you do neutron scattering, the lambda is about 2 nanometers, right? But the angle could be very tiny because the neutron scattering, for example, the detector is about 30 meters away. They are not very close. In light scattering, it's only a half a meter away or 1 meter away. So when you have a detector at a very large distance, the detector is far away somewhere there, then I can measure accurately even with the small angles. So in neutron scattering, typically the angles are very tiny. Similarly, for X-rays, the angles are tiny. But for light scattering, angles are like 90 degrees, 45 degrees, 20 degrees, and things like that, right? So therefore, depending upon the contrast factor between the different components of your system, which is responsible for this prefactor here. The scattering intensity is going to depend upon there is a contrast factor which connects the scattering intensity and form factor. In the case of light, the contrast is coming from refractive index. In the case of X-rays, it comes from electron density. In the case of neutrons, it's a scattering length between hydrogen and the deuterium, for example. There are different scattering lengths. So I don't want to get out of our introductory concepts about how we use them. Technically, we can talk about it another time, right? But right now, we just deal with this combination of lambda and theta for K. Now, the question to you is, okay, what does this mean? Look at this lambda. Lambda is a length, right? 500 nanometers. And K is coming like 1 over lambda, 1 over length. So I could write this K, right, is kind of a 1 divided by some observational length. Depending upon your system. Okay, so this I will identify scattering wave vector to be 1 over the length scale. When I choose some number here, K, that is basically reciprocal of the length scale I'm looking at. Length scale I'm going to probe. That's the meaning of this K. Whenever we talk about scattering, yeah, there's a formula for that. There's a formula. There are lots of books written on them, but that's not the way we want to think for the time being. We want to think K is a measure of my yardstick. It gives me, suppose I have one particular K, I can explore this length depending upon K, right? Or I can explore this whole length, chain length, depending upon K. So for example, suppose I have a system, suppose I want to explore a chain like this. Suppose I want to know something about the size. That's my goal. Then what I need to do is I need to send tune my scattering wave vector in such a way. Oh, I'll use a different color. Right? I want to send in a beam which is like this. That is, this is my observation length. Okay, that's my observation length. That means that is 1 over K, corresponding to 1 over K. That is, I want to have, if I want to measure the size of the molecule, I want to have this 1 over K larger than the size of the molecule. Let's say this is my RG. This is my RG. I want to have, in order to get this, I want to have 1 over K, which is my observation length, is larger than RG. That makes sense, right? Because if you want to measure something, you need a yardstick which is bigger than that to measure that, right? So my yardstick has the observation length of 1 over K. So I want to have a situation where 1 over K is larger than RG. This means K times RG is less than 1. That's what this means, because I bring K to the right-hand side, say K RG is less than 1. So if I want to measure the size of the molecule, I should be in the regime of K times RG is less than 1. Only then I can measure it, okay? Now, having gone through this discussion, it makes sense. I go back to Debye formula. I say K times RG is less than 1. Only then I can measure molar mass and radius of gyration. I will not be able to measure molar mass by looking at a yardstick, which is tiny, all right? So I go back here. Suppose I'll draw the chain once more. This is my chain. And suppose I have my beam, my scattering wave vector, observation length is like this. So this is my observation length. Then when I have an observation length shorter than the size of the molecule, I do not measure the size of the molecule. Instead, what I measure is what is happening inside the polymer chain. So here I interrogate internal structure of this object. Okay. So here I can measure, right? I can measure, this gives me internal structure. In this limit, and that limit corresponds to, remember this is observation length 1 over K, 1 over k is smaller, right? 1 over k is smaller than RG because RG is this big, as I have drawn. RG is very big, but this observation length is shorter than RG. This means, what does that mean? So this means k times RG is greater than 1. That's the limit that we are in. Not a surprise, because when I go in here, right, k times RG is larger than 1, or k square RG square larger than 1. I don't measure radius of gyration or molecular weight, but instead I measure this quantity, 12 over k square over F. Now I must make an important statement. In general, although we derived it for Debye structure factor, in general, this quantity can be written as 1 over k power df. Remember, I introduced fractal dimension, df is equal to 1 over mu. In general, I'm not going to go into the derivation. In general, we can show that the form factor goes like 1 over k to the power df, fractal dimension, in this limit. And you know that the fractal dimension is 1 over mu. You know that already. We know that. Well, no wonder it's a 2 for the Debye structure factor, because it's a Gaussian chain. We know that for Gaussian chain, mu is equal to half. Therefore, df is equal to 2. Therefore, I get 1 over k squared. In this case, I know that 12 by L square we can calculate exactly, but the important punchline is this behavior at a larger values of k times Rg gives me the fractal dimension. It gives me the fractal dimension. Okay? And that is, fractal dimension means how they are put together in this polymer chain, how they are put together, or how they are put together in this assembly. This argument is valid not only for a single chain, even for large assemblies, which we'll talk about later. Yeah. Okay, so what I like to do is, and I'm going to make a conclusion on this technique, how we do the measurements and how do we relate to them. Okay. And June Fang, you are always welcome to interrupt and ask me some questions. On behalf of your students, if you have any questions, you are welcome to ask. I know that Dr. Dija has joined, and you guys can talk about it. You are welcome to interrupt and ask me if something is not clear. All right, I would invite you to ask questions. So before that, maybe I'll allocate a few minutes towards the end, and let me summarize what I just said. I go back to this formula, right? And then I take this, right? And I take the scattering intensity. And let me go to the limit of, I want to do two limits. One limit is k times Rg is smaller than 1. Okay? Now I'm writing in general. I'm not putting the 0 because the theorem that I showed you is true for all cases. Therefore, I don't have to put a subscript 0. This is a very general result. K times Rg is smaller than 1. In that limit, and I told you I of k is proportional to the form factor S of k, and that's equal to n 1 minus k squared Rg squared divided by 3 plus etc. True in general. So this means, and it's also small, all right? That means 1 over I of k, that is, I take this and I take the reciprocal, and that's going to give me 1 divided by n, right? And then 1 plus k squared Rg squared divided by 3 plus etc. Remember, 1 divided by 1 minus x is equal to 1 plus x plus etc. Right? You know that, right? So that's all I have done. I have taken the reciprocal of this. Okay? Therefore, if I plot 1 over I of k versus k squared. Okay, which is, you guys know that that's equal to sine square theta by 2. Forget about lambda and everything. It's proportional to sine square. K, as you know, k is 4 pi over lambda sine theta by 2. Therefore, k square is sine square theta by 2. Okay, we have that sine square by theta by 2. If you do this, what you will get is you'll get a straight line. You'll get data. You'll make measurements. Then you'll get a data like this. Something like that. Clearly, I cannot make measurement at the k is equal to 0. Because when k is equal to 0, that means the theta is 0, right? When you take a theta to be 0, the incident beam will damage your detector. When theta is 0, k is equal to 0. That limit we cannot do practical. For all practical purposes, you can't do it, right? You should not, please don't try it, all right? Because when theta is equal to 0, you'll burn your instrument, right? So therefore, what you have is you have data for small angles. Still, we are in this limit. K times Rg is less than 1, right? Then you connect them, you extrapolate them. You extrapolate them to give me intercept. That intercept is 1 over n. So you get the molecular weight. Then you get the slope. From this, also, you get the slope here. Slope. And then you can tell the slope. That slope is Rg squared divided by 3n. You know n, therefore you can get Rg. So from the slope, you can get radius gyration. From the intercept, you get molar mass, 1 over molar mass. And this is the way you determine molecular weight and radius gyration. Okay, for any system, provided you have this condition met. If you do not get a straight line here, right? Suppose there's a curving, then something else is happening in your system. There is some aggregation going on, or you are not satisfying this condition, right? Etc. etc. So you need to be very careful about when you can rely on your data by precisely looking at the nature of this and looking at the condition when this is valid. Now let me go to the other limit. The other limit is, as I pointed out, k times Rg is larger than 1. This is the other limit. Right? In the other limit we discussed, that is going to have this limit. K times Rg is larger than 1. Only internal structure can be gotten. And we argued that it can give me the fractal dimension. And I'm telling you, S of k goes like 1 over k to the ds. Okay, so then in this case, I say I of k goes like S of k, and that goes like 1 over k power 1 over nu. Okay, that's df. 1 over nu is df. So what we get then is, let me take a logarithm of this, right? The logarithm of I of k versus the logarithm of k, you should get a straight line. And that slope is equal to minus 1 over mu. Okay? And I hope you are able to appreciate the beauty of the situation that we have, right? Single chain, completely freely jointed chain, and we come up with a formulation of how to measure, how to determine molar mass, radius gyration, fractal dimension, size exponent. If I want to know size exponent, there are two ways to go about. One is to use this technique. That is, you go to observation length small. Observation length is small. So you're going inside the polymer chain and make measurements with that condition, satisfying this condition, and then plot, double logarithmic plot, scattering intensity versus k, and the slope gives me minus 1 over mu. Then I know determination of size exponent. Other way to do is, I make multiple samples with a different molecular weight, same molecule, same solvent. I measure the molecular weight and measure radius gyration using this technique. Then we know this is a formula that we had, which is Rg is proportional to Rg is proportional to n to the nu, right? Rg is proportional to n to the nu in general. In this particular case, nu turned out to be half, but in general, it's going to be some size exponent. So I know n for different values, and I know corresponding values of Rg. Then from there, from that relation, I can determine nu. And at the end of the day, when we do all these things, they'll all be consistent. Whether I get a nu from this multiple experiments here, or I get from this experiment, I should get the same answer. So they're all consistent checks, right? You do small angle experiment where k Rg is small. You see large angle, that is k times Rg is large, and then you analyze this data for different molecular weights, different Rgs, then the picture must be absolutely consistent. When we do that, we are in very, very good shape of fully having characterized a polymer chain. Okay. Now, I'm telling you again, for a Gaussian chain, right? For a Gaussian chain that we composed, Kuhn chain completely, I'll show this model once more, completely freely jointed chain, right? Completely freely jointed chain. I'm telling nu is equal to half. That's what the model predicts. We just did this, right? This is what the model tells us here. Nu is equal to half. Rg is proportional to square root of n. Do you think it's possible, right? Do you think this model I built, the Mr. Kuhn built based upon Einstein's idea of random walk, is completely freely jointed? Is this possible? There's no extra volume at all. They don't hit against each other, nothing, right? Is it realistically possible? I think this is crazy, right? I would think if I'm an alien who comes to this planet and somebody tells me a polymer chain is going to be completely freely jointed and it's more phantom-like, there is no interaction whatsoever, I would say, oh, no, this planet is not quite right. This planet seems to be quite wrong, right? That's what I would think. Now I'd like to share with you some experimental data, okay? Because I want to check our ideas here. So how do I share with this experimental data? So I go to, I have given this handout to you already. So let me go and check. Where is that? Oh, here it is. Look at this data. This is a polystyrene in cyclohexane at 35 degrees Celsius. Polystyrene in cyclohexane at 35 degrees Celsius. And some of those dots correspond to same polymer, but a different solvent, decalin. You folks know decalin is different from cyclohexane, right? And then, of course, we know that the temperature is different here. For decalin, the temperature is 15.2 degrees Celsius. For cyclohexane, 34.8 degrees Celsius. And they are plotting, this is Professor Berry. He is plotting the radius of gyration based upon the measurements of the type I showed you as a function of molecular weight. This is double logarithmic plot. Remember Rg, I told you Rg it goes like n power nu. For this model, that is half. And n is proportional to number of Kuhn segments, right? That's proportional molecular weight I told you. So therefore, Rg as a function of molecular weight in a double logarithmic plot will have a slope of half. That's exactly what they see. This is very interesting. Why is it interesting? Do you believe that polystyrene cyclohexane 35 degrees Celsius is going to be interpenetrating? The chain is going to cut across, right? Violating uncertain principle for electrons, that the two monomers cannot sit on the same place at the same time, right? But our model is the Kuhn chain model, Gaussian chain model, where Rg is proportional to square root of n. But experiments show that that's indeed the case. Let me show you one more experiment. Right? One more experiment is this experiment. Right? And they have plotted a scattered intensity times theta squared and as a function of theta. This is X-ray scattering. Right? This is X-ray scattering. They used X-ray scattering in this reference. And then scattering intensity times theta squared does not depend upon theta. For a Gaussian chain, we talked about this. I of k goes like 1 over k squared for Gaussian chain. If you are in this regime, k times Rg is larger than 1. Since you are doing X-ray scattering, k, the wavelength is very small, therefore you are able to satisfy this condition. In X-ray scattering, you can do this. Although the angle is very small, the wavelength of X-rays is very tiny. I showed you before. Wavelength is, right? The wavelength is like a 0.15 nanometers. And therefore, you satisfy this condition, although this is a small angle here, because it's a combination of lambda and theta which dictates the scattering the vector. Therefore, in this particular case, since the angle is small, the k is going like simply theta by lambda, if you like. Lambda is wavelength, right, of the X-rays. Now theta, sine theta is for theta small, sine theta is a theta. Therefore, this goes like 1 over theta squared. Therefore, if I plot I, which is k, is a function of theta, times the theta squared, it is a constant. This means, right? This means here, this means nu is equal to half. That's why we have 1 over k squared. This is a device structure factor. Nu is equal to half. There is a fractal dimension 2, nu is equal to half. So therefore, when they plotted theta squared times I theta, please remember, this is polystyrene in cyclohexane at 35 degrees Celsius. That's what they had. Polystyrene, cyclohexane at 35 degrees Celsius. That's where they got that exponent. Now, this is a small angle experiment, right? They measured Rg, they measured N, and then they looked at the exponent. But here, one shot, they took a molecular weight of 2 million, with some small concentration of polymer, and then they measured the scattering intensity as a function of wave vector, and then they get this flat region. This means nu is equal to half. Okay. So it is consistent, right? We took polystyrene cyclohexane at that temperature, then you get whether you do this region, k times Rg is much larger than 1 region, or in this region, this is k times Rg is much less than 1. That's the way they got, because you have to satisfy that condition. K times Rg is less than 1, you get this one. And then when k times Rg is larger than 1, you get this one, right? Either you do this experiment or that experiment, you get same value. But the surprising thing is the Kuhn chain model, where we ignore extra volume interaction, where we ignore any orientation of the bonds, freely jointed chain, how come we observe that prediction? We observe it, they are facts. Right? What happens? So what I like to do next is I like to look at the role of extra volume interaction. I want to see how the different parts of the chain interact, and I want to look at the consequences of that one. And then see why do we observe these things, and how delicate this one is, or is it universal? All the time is what we will get, etc., etc. And that will be augmenting our understanding of characterization of polymers in solutions. Okay. So, Junfang, I think this probably is a good place to break, because the other topic will take us a little bit further, a little bit more into a long discussion. And so I would like to invite you all to ask me questions, because we still have 5 minutes. Right? And I would really invite you to ask any question that you may have right now.
Anyone have a question? Hi, Professor.
Yes.
The students may need some more time to realize the lectures.
Okay. No problem. Well, if there are any issues, you let me know, Junfang, right? You can also talk to Dija, right? I mean, you can contact me, of course, Junfang, right? You could let me know, right? But I don't know whether it is custom for people to ask questions, in a lecture, right? I do not know, but I would invite you, your students, to ask questions if they wish to, right? During the lecture, because that way we all understand better, right? So that option is available to you, but let them take time, all right? And I'm going to send this recording right away as soon as I receive it, and then they can also listen to them. And there is also a handout. I sent you these PDF files, right? You have that. And I'm writing down on my iPad to explain more, which I notice people are taking notes. I know that. So however way we can enhance it, we can do it. All right. So I'm going to stop the recording right now, and then we can chat a little bit more, right? How about that, right?
Okay. Thank you. I think we may have more time to